Hello, this is Team 1072, and we decided to focus on Problem B. To sort of outline our presentation, we will first be introducing the problem and motivation for our models. Next, we will introduce a modified Markov chain model, and then we will introduce our linked discrete distribution model. And finally, we will discuss strengths and limitations of our solutions. Problem B basically focuses on the issue of AI model collapse, which has been shown to occur when new generations of models are recursively trained on the output of previous generations. And we are specifically focusing on what behaviors arise over time when multiple AI models interact with both human and AI-generated content over many generations. This is an important problem to consider, especially as AI use becomes widespread and more content online becomes AI. In fact, recent sources, such as a recent Europol report on deepfakes, predicted that up to 90% of online content could be AI-generated by next year. As Shumailov and others from the given 2024 paper on AI model collapse explain, collapse is typically attributed to three sources of error. The primary source of error is statistical approximation error, which explains that information is lost due to the finite size of sample data. The two secondary errors are functional expressivity error, which explains that neural networks are unable to capture the full complexity of a distribution due to their finite size, and functional approximation error, which explains that learning algorithms utilized by machine learning procedures are imperfect. Our model should be considered in the absence of the functional approximation and expressivity errors. The paper also discussed two special cases of model collapse: early model collapse, where the tails of the distributions are lost, and late model collapse, where distributions collapse their delta function. The Markov chain model focuses on early model collapse, while our linked discrete distribution model focuses on late model collapse.
Our goal is to simulate how multiple AI models evolved when repeatedly trained on mixed human and AI-generated data, and seeing if the use of multiple AI models can prevent collapse when it's trained on its own AI-generated data. In this situation, we have two variables, I and N, where I is a number of AI models, numberth of AI model, and N is a numberth of generation. So in this situation, we want to get the overall probability distribution of all the AI models. So we take the average of all the AI models from I to 1 to M, and then we get the final value, Q AI of N, which is a probability distribution of all the AI models, the average of all the AI models at the nth generation. Then we plug it into a formula to get the probability distribution that the next AI is going to train on, which is a summation, which is a weighted sum of both the AI probability distribution of the Q AI of N and P naught, which is the probability distribution of the original human data. So then we could tell that then the next AI data, the next training set for the next AI, will have a mix of both the synthetically artificial data and real human data from P naught. Then we take this P of N, we take this probability, the training distribution that we just generated, and we plug it into a learning function, f of I. The learning function depends on the AI model, that's why you have the subscript I. And that outputs Qi of N plus 1, which is the probability distribution of that ith AI model at the generation N plus 1. Then what we do is we plug in this average Q AI of N function to get a final P of N equation. We equate the right-hand side to a transformation of P. And finally, we get this final Markov chain equation, which is P of N is equal to the transformation of P n minus 1. And we see the current probability distribution of an AI model depends only on the probability distribution of the previous AI model, where P of N is a distribution of the generation N, P naught is a true human data, F of I is a transformation by model I, M is a number of models, and alpha is a fraction of AI-generated data. Finally is the results. We wanted to see the difference between using a single versus using multiple AI models. The first one is tail coverage, which is the retention of tail information as the model generation progresses. As we see, as the number of AI models go from 1 to 5, it increases the ability to retain the tail information with multiple models. A very similar thing happens as quality drift, which is the ability of the model to accurately describe the initial data. As we see again, using multiple models allows the data to be accurately retained as the number of generation increases.
We will now be going over the linked distribution model. For our assumptions, we first assume that 50% of the dataset is generated from humans. We also assume, as stated before, that functional expressivity error and functional approximation error are not present. That is, we are only considering statistical approximation error following the paper. Additionally, we assume that all AIs use the same size of training dataset, that each task is in the same distribution family, namely geometric, and that tasks are distributed according to the binomial distribution. For the simulation setup, we consider two probability distributions: an overall task distribution, where pi of t is the probability of getting a certain task in this space. This is distributed using a binomial distribution with p equals 0.5. Additionally, there's another distribution for each task, where x is the complexity for a given t task. This is distributed using a geometric distribution, and it is dependent on the pi base distribution for tasks, where each p is equal to 1 minus the probability of getting that task. This is to ensure that rarer tasks have a higher likelihood of being more complex. This leads us to our simulations. First, we ran a single AI simulation using 100% AI data and 0% human input to try and see if the model simulates what was theoretically shown to happen in the paper. As you can see in figure 4, after only 10 generations, the model becomes very, very close to a Dirac function around task 15, which is what AI was trained on this simulation, showing support for the results in the paper. As for our complete results, when we are considering a complete AI saturation of a space, as you can see in figure 5 for tasks 20 through 80, this results in a uniform distribution with a peak happening where the normal center would be. We think this is likely due to how each individual AI model moves towards collapse in the long term, and then when taken as a group of AI models in the space, this forms a kind of uniform distribution with each Dirac accounting for a singular task. As for the center peak, we think this is due to the continual reintroduction of human-generated content, which has a very strong peak in the middle and then falls off for rarer tasks. Additionally, as you can see in figure 6, when testing with groups of AIs, each individual group forms its own uniform distribution, but has very little effect on the overall shape of the space, rather than just reducing the probabilities and sizes all around. For strengths, the model considers AIs trained on different tasks, and even how AIs on the same task can interact. And additionally, the model can, in the future, include functional errors. And as for limitations, the choices for the distributions are somewhat arbitrary, as are what tasks and complexities actually represent. We also assume that all AI models are trained in the same way, which isn't really representative of real life. Additionally, since the tasks and complexities are somewhat arbitrary, there's no practical output given for what each AI in the end is outputting.